Hello, my name is Muhammad Fazli Zalikram, and today I will be presenting an overview of analog and digital modulation techniques. In our modern world, we constantly transmit voice, data, and images over long distances. But how do these signals travel through the air or cables without getting lost? The answer is modulation. Modulation is the process of varying a high frequency carrier signal to match an information signal. This is crucial because it reduces noise, improves range, and helps us use bandwidth efficiently. So today we will explore two main categories: analog modulation, which uses continuous signals like in traditional radio, and digital modulation, which uses discrete bits 1 and 0 as common in our smartphones and Wi-Fi today. For section 1, analog modulation. Let's start with analog modulation, where a continuous message signal varies a parameter of a carrier wave. Amplitude modulation AM. In AM, the amplitude of the carrier changes based on the message signal, while frequency and phase stay the same. How it works: an AM modulator uses a carrier oscillator and a non-linear device like a diode to combine the signals. For the demodulation, we use an envelope detector, a simple circuit with a diode, capacitor, and a resistor to recover the original message. For application, you will find AM in aviation communications and long-distance MW radio broadcasting. Second, frequency modulation, FM. In FM, we keep the amplitude constant but vary the frequency. How it works: we often use a voltage-controlled oscillator. As the message voltages goes up, the frequency shifts. For the demodulation, this requires a phase-locked loop or frequency discriminator to turn those frequency shifts back into sound. And for the application, FM is our standard for high quality music, broadcasting, and TV audio because it's much more resistant to noise than AM. Now, let's look at the backbone of the digital age: digital modulation. For the first one, amplitude shift keying, ASK. Think of this as a digital version of AM. In its simplest form, on-off keying, the carrier is on for a binary 1 and off for a 0. For the circuit, it uses a digital switch to control the carrier. Application: it's used in low-cost wireless systems and fiber optic communications. For the second, phase shift keying, PSK. Here we change the phase of the signal. In binary PSK, the phase flips 180 degrees to represent a 0 or a 1. For the demodulation, this is more complex because it needs coherence detection, meaning the receiver must be perfectly synchronized with the transmitter. For the application, because it is highly robust against noise, PSK is used in Wi-Fi, cellular networks, and satellite communication. So how do they stack up against each other? First, bandwidth efficiency. Digital modulation wins here. It can pack much more data into a limited frequency range. And the second one is noise resistant. Digital is much stronger since the receiver only looks for discrete states like 1s and 0s. It can generate the signal even if there is background noise. Complexity: analog systems are simpler and cheaper to build. Digital systems require complex processors and synchronizations. Last but not least, practical use. Analog is mostly for legacy broadcasting, while digital dominates everything from our mobile phone to the internet. To wrap up, modulation is the fundamental process that makes long-distance communication possible, while analog techniques like AM and FM pave the way with their simplicity. Digital techniques like ASK and PSK are the future due to their superior noise immunity and efficiency. The choice ultimately depends on the job, whether we need a simple range of an AM radio or the high speed data of a 5G network. Thank you for listening.